In this last section of Chapter 8, we're going to take a look at what are called improper integrals, and they might not be something that you think they are. I know we've kind of used the term improper integral before when we've written an integral, say where this is 1 and this would be maybe -2, and then of course we kind of said, well, that's not proper because we really need it to be -2 to 1, where the smaller number's at the bottom. And of course we put a negative in the front of that. So I think we've kind of used that word before to call this kind of an improper integral because of the bounds, but this is a little bit different with regard to something that is called an improper integral. Okay, so what exactly is an improper integral? Well, there are two types of improper integrals, and as the title of this slide says, we're going to look at the first type of improper integral. And to help us kind of understand what that integral would look like, let's answer this question. Starting at x equals 1, what is the area of the region under the curve of the function 1 over x? So you can see that graph drawn here, and we're going to start at 1, and we want to find the area under the curve from 1, under the curve of 1 over x. So there's an interesting thing not being mentioned here, and that is where we're stopping. And it turns out we don't want to stop. We want to find the area from 1 to infinity. So of course I think everybody's first inclination here, at least for a guess at an answer, would be of course infinity. But let's see how this kind of all plays out. So let's first set up an integral. Even if this was the integral from 1 to 2, we would still have to set up this integral. But in this case, we're not stopping, so we're going to set up an integral from 1 to infinity of our function 1 over x with respect to x. So we have to put that dx. This symbol that we use for infinity, just note, is not a number. It's an idea. It's an idea of increasing without ever ending, increasing without bound. And this is what is called the first type of improper integral. If you ever have an integral where either one or both of the endpoints are either positive infinity or negative infinity, we're going to be looking at what is called an improper integral, which is going to require a different technique in terms of how we approach it. So how are we going to approach this problem? Well, we're instead not going to go out to infinity. You'll notice in the animation down here, I kind of took out the red that kept on going here, and I'm going to chop it off. I'm going to chop it off at some value b. What could b be? It could be 10, it could be 20, 30, it doesn't matter, but it's for sure a number. So we're going to be taking this integral now from 1 to some other constant b. But luckily that b is a number, so it's not like infinity, which is of course making this integral improper. Okay, so let's go ahead and take this integral. There's nothing too special about this. The integral of 1 over x dx is ln absolute value of x, but just to kind of skip that step, since we're dealing with positive numbers here, we don't have to put that, but just note, technically it's ln absolute value of x. We're going to put that bar notation so we can apply the fundamental theorem of calculus. Plug in the top bound, plug in the bottom bound, subtract, and of course ln of 1 is equal to 0, so that just goes away. So it turns out the area is ln b. So the funny thing is, if for some reason we wanted to find the area from 1 to 10, then that would just be ln 10. If we wanted to find the area from 1 to 1,000, it'd be ln of 1,000. But of course, we don't want to stop at 10, 20, 1,000, a million. We want to go on forever. So what we want to do is to ask ourselves the question, what would happen if that b goes to infinity? Because that's where we want it to go. We don't want this area to ever stop, so of course we want b to go to infinity. Up until this point in this class, we've certainly used a very specific concept that allows us to take values to certain other numbers, or in this case, the idea of infinity. And that would be a limit. This right here is very important in terms of when you're doing these problems. When you're doing these types of problems, we have to set up what is called a proper integral. And the only thing that really this requires is that we take that upper bound of infinity and make it something more reasonable, so to speak, in that we're going to call it a value b, and then we're going to take the limit of that integral as b goes to infinity, which makes sense because we want b to eventually go out to infinity and never stop. So that's going to be the key. Anytime you're doing these problems, you need to set up a proper integral. I'm just kind of breaking this down into some steps here so we can understand what's going on. Okay, so of course we already did the integral part. I hope you can kind of realize there's two operations going on here. We're doing the integral part first, which I'm trying to box here or bracket here in blue. So we got to do the integral part first, then we can apply the limit, just like an order of operations sort of problem. So we know the integral part was equal to ln b, and now we need to take the limit as b approaches infinity. Well, luckily that's just a matter of plugging in, so to speak, infinity. The natural log of infinity is infinity. So what did we discover? Well, we discovered that the area under the curve from 1 to infinity is infinite. And I hope that probably shouldn't really be much of a surprise to us. Of course, if this area keeps on going forever and it never stops, then of course that area should be equal to infinity. Because this integral is infinite, because we got an infinity for our answer here, what we can say about this integral is that it diverges. This term diverges is going to be very important as we transition into chapter 9. So be sure that you kind of take in this idea of what diverges means. And really all diverges means in this particular case is that we're not approaching a specific number. And if this little road sign kind of helps you out where we're branching off and not approaching some specific area, hopefully that'll kind of help you remember what the word diverges means. This integral, since it's infinite, we say that that integral diverges again because it does not approach a specific number. Okay, so let's take another look at a similar example. And in this problem, we're going to start at 1 again, and we want to find the area of the region under the curve 1 over x squared. So different function than before, but still the same idea. We want to start at 1 and find the area from 1 to infinity. Again, this falls into the category of an improper integral because one of our bounds, or it could be both of our bounds, but in this case one of our bounds is either positive or negative infinity. So we're going to go ahead and set up this improper integral first. We want to integrate from 1 to infinity of 1 over x squared dx. So just like we saw before, what we can do is consider a different integral. You'll notice down in our animation again, I'm going to go ahead and stop my area at some constant we're going to call b. Why b? Well, I guess usually we're integrating from a to b, and since we don't know what this upper bound is, maybe b is an appropriate letter to use, but it really doesn't matter what letter we use here. All we need to realize is that we're using a letter to stand in the place of a constant, because that would be okay in terms of us writing an integral. We're always integrating from one constant to another constant, but in this case, we don't know what that constant b is, but we certainly don't want it to be infinity. Okay, so be careful here. Don't kind of get too wrapped up in all these ln integrals that we see a lot. This one's not a natural log integral. This one we can rewrite integral friendly as x to the negative 2 power, but when we add 1 and divide by that power, we'll end up with negative x to the negative 1 power, and of course we can simplify this, and I kind of skipped this step here, but we can just simplify that to negative 1 over x, and of course the bar from 1 to b. When we plug in the b, we'll end up with negative 1 over b. When we plug in the 1, we'll end up with negative 1 over 1. And again, we have to subtract those two values by the fundamental theorem of calculus. When we clean this up a little bit, the negative and negative become a positive 1. So I'm going to just move that to the first position. So it'll be 1 minus 1 over b. So again, kind of the interesting thing here is if you wanted to find the area from, say, 1 to 10, we would plug in 10 for b, and that would be the area. If we wanted to find the area from 1 to 1,000, we'd plug in 1,000 in for the b, and that would be the area. But we don't want that. We don't want to ever stop. We want to let b, again, go to infinity. So the key here for these problems, just like I said before, and it's the thing that it's going to be looked for in these kind of AP problems, is that you set up what is called a proper integral. It's very tempting to leave that infinity in the integral symbol and just kind of do it that way and just make it work out. But what we need to do is set up one of these proper integrals. And really all it involves is you replacing that bound that makes it improper, which was of course the infinity, and replacing it with some letter. Here I called it b. And then of course we want to take the limit as that letter goes to infinity, and again here we're choosing the letter b. So again, I kind of broke this into two steps. I went ahead and already figured out what the integral portion of this problem is. And again, remember there's an order of operations here where we need to figure out the integral portion first, and then we can apply the limit. So that's what we need to do here. We want to take the limit as b goes to infinity of 1 minus 1 over b. And if you think about what that would really mean, that would mean plugging in infinity for b, 1 over infinity, or really any number over the idea of infinity, is approaching 0, so it's equal to 0. And of course 1 minus 0 is 1. So this might be a bit of a head scratcher, so to speak. I think for most of us, just like in that last problem, we would have gone, okay, well, if the area goes on forever, we should get an infinite area. But as it turns out, and here's one of the fantastic things about math, that it produces unexpected answers sometimes. It turns out that the area from 1 to infinity under the curve of 1 over x squared is actually just the number 1. So a very, very interesting idea that I think takes some time to kind of sit down and come to terms with. The area of this infinitely long region is finite, and it's equal to the number 1. I guess another way to look at this, to kind of even give you more of a concept to think about, is you'll notice if I make a box right here, a little square in this 1 by 1 region, 1 unit up, 1 unit across, this area right here, of course, would be an area equal to 1. It's a square that's 1 by 1, so the area is equal to 1. So as it turns out, both of these two regions have the same exact area. That is to say, we could take all of this orange stuff that goes on and on and on forever and actually fit it inside of this little square to the left right here, because they have the same area. So again, a very strange outcome that I don't think many people would really have guessed would be possible. But as it turns out, the area of this infinitely long region is 1, and that area could actually fit in this square that you see here in purple. Whenever you get an integral that turns out to be a finite number, it turns out that we call that integral a converging integral. And all that means is that our integral approached a specific number. We got some sort of finite number, so what we do is we say that integral converges. And again, just like I said in the last slide, diverging and converging are going to be very, very important words in our vocabulary as we transition into Chapter 9. Okay, to keep on practicing this first type of improper integral, here we want to find the integral from 0 to infinity of e to the negative x dx. Again, we don't want to go out to infinity, so what I'm going to do is just put a b. You can see it over here in the picture. I'm going to go ahead and put a b there just to show that I'm stopping this area at some point. We don't know what the value of b is, but we at least know it's a constant, so we can get that infinity out of that integral, because it's improper to leave it there. Of course, we need to set up a proper integral, so we need to take the limit as b goes to infinity of this integral. So again, remember, there's a bit of an order of operations going on here. We first need to address the integral portion of this problem, and then we can take the limit. So let's go ahead and address the integral portion of this problem. The integral of e to the x is e to the x, but that's only if we have a plain x as a power. Since this is a negative x, we're going to have to approach this as a u substitution. And if we do that, it's fairly simple. We'll end up with du equals negative dx. There is no negative over in our integral problem. So of course we can move that negative over and we'll be left with this integral. We'll of course move the negative to the outside of the integral, and then we'll just have e to the u du. That integral is nice and simple and straightforward. The integral of e to the u is itself, and I'm going to just plug that u back in the same step. So we'll be left with negative e to the negative x, and then we need to evaluate that at b and 0 using the fundamental theorem of calculus. Again, we need to write this limit notation every step of the way because we haven't taken a limit yet, so just be careful with your notation skills here. Okay, so let's plug in the top bound. When we plug in the top bound, we'll end up with negative e to the negative b, and when we plug in the bottom bound, e to the 0 is just 1, and I guess technically I'm kind of skipping a step here, but that was really minus 1. Remember, we need to subtract away the bottom bound when we plug it in, so we'll end up with a negative 1, but the two negatives of course become positive. Okay, so after we've done the whole integral portion, now we're ready to evaluate this by the limit. So what is this limit equal to? Well, we're going to have to recall some special limits here. We know that when we plug in infinity, we're going to have e to the negative infinity. E to the negative infinity is just 0. I left the negative in front of the 0, which is a little redundant in a way, just so you could see that the portion that is e to the negative infinity is 0. And then of course, I guess that negative in front of the 0 really doesn't matter. When we take the limit of that constant, it's still just 1. So of course, 0 plus 1 is just 1. Anytime an improper integral turns out to be an infinite answer, we say it diverges. In this case, we found that it's a finite number, so we're going to say that this improper integral converges. Okay, here's a little tougher first type of improper integral. Here we want to find the area from negative infinity to infinity of the function 1 over x squared plus 1 dx. So, in this type of a problem, we're going to exploit the fact that there's some symmetry going on here. I'm going to pick a point to split this area into two parts. They don't necessarily have to be equal parts. In other types of problems, it might not have symmetry, so you might have to split this into two pieces where there is no symmetry. Luckily, here there is symmetry, but I'm still going to do this as two separate pieces. Theoretically, I could just find, I guess, the right side or just the left side, and then multiply that final answer by 2. But instead of doing that, for the sake of seeing how to set these up, maybe if there isn't symmetry, what we're going to do is split this area into two pieces. Of course, I'm going to split it right at where the symmetry happens, because of course that's convenient in a problem like this, at 0. So we need to set up two separate integrals. We're going to set up an integral from negative infinity to 0, which will be the left half. And then of course we're going to add to that the integral for the right half, which would be 0 to positive infinity. Just like you saw in the previous examples, and really this is just two problems in one. Don't kind of get overwhelmed with all the stuff you're about to see here, because I'll be honest, it's going to get a little messy, but really just appreciate this is just two problems in one. And then again, we're going to add those two answers to each other once we figure out what they are. So let's go ahead and do both of these pieces to put these answers together. I'm going to go ahead and call this very left end the letter A, and then this very left end the letter B. Remember, we don't want to go to negative infinity. We need to chop it off at some point, and that letter I'm going to call A. On the right side, just like you saw in the previous examples, we can't go out to positive infinity. We have to stop this area at some constant, and that I'm going to just call B. Once we do that, we can now just set up the two proper integrals here. For our first, or our left side of our picture here, we're going to take the limit as a goes to negative infinity, of the integral from a to 0. And then for our right side of our picture here, we're going to let b go to infinity. And that integral, of course, is now going to be 0 to b. And that makes sense. If you kind of think about plugging in negative infinity for a, we get the thing we see above here. If we think about plugging in the infinity for b, we get the integral we saw above here. But of course, we don't want to do that because that's an improper integral. Okay, so luckily, once we know how to integrate both of these, it's the same for both of them. So let's talk about this integral. Can we simplify this fraction? Unfortunately, no. We have terms in the bottom here. We can't split up this fraction. Can we use a u substitution? Well, I'm going to write this in real quick just so you can see it in case you're not able to do it in your head. But if I call the bottom u, we'll end up with 2x dx. And the problem with that is we don't have an x in the top of our fractions here. So we can't do a u substitution like that for this problem. Once we exhaust those options, you have to recall there's one other form of integrating that we've seen, and it dealt with our inverse trig functions. The integral of du over u squared plus a squared is what you see over here involving arctan. And luckily, this is the most basic of them all. You can see that the u in this case would be x. You can see also in this case that the a would be 1. U squared is really x squared. A squared is really 1 squared. So then that would mean this integral is equal to 1 over 1. So I guess technically there's a 1 over 1 in front of the arctan. And then arctan of u over a. Again, u is the x. And we're dividing that by 1, so I guess we don't have to put division by 1, so we're just going to keep it nice and simple. Don't forget, we have to put that notation from a to 0 because we still have to apply the bounds. Luckily, once we did that first integral, the other one is exactly the same. Okay, so again, remember there's a bit of an order of operations here. We got to figure out the whole integral part, then we can apply the limit. So let's go ahead and figure out the integral part and apply the fundamental theorem of calculus. To save some space, I kind of skipped a step here, but when we plug in 0 here for arctan, that's going to give us 0. When we plug in a, of course, that's just going to be arctan of a. So I guess technically it's up to you if you want to squeeze it in. I'm going to erase this here in a second, but technically we have 0 minus arctan of a, because arctan of 0 is 0. For our other integral, we'll plug in the b first, which will be arctan of b, and then just like you saw before, arctan of 0 is just 0. So instead of putting a minus 0 here at the end, it's just, of course, a lot easier just to leave it as arctan of b. Okay, after that, now might come the harder part. What is the limit as arctan goes to either negative infinity or positive infinity? And that probably has been the hardest limit you've had to think about up to this point in this class. They've been fairly simple and straightforward, but this one might be a little tougher. So let's go ahead and take a look at a picture of arctan to maybe see how easy this is, assuming you know what the picture of arctan looks like. So let's talk about this first limit right here. I want to figure out what the limit of arctan is as it goes to negative infinity. As this graph goes out to negative infinity, is it approaching a particular y value? Well, yes, you can see the horizontal asymptote down here is negative pi over 2. For the second integral here, we need to figure out what's happening as arctan approaches positive infinity. Well, as our graph approaches positive infinity, you can see again it's approaching the upper horizontal asymptote, which is positive pi over 2. So probably without that picture here for arctan, these two limits would have been fairly difficult to figure out. But now that we have this picture, we can see that yet again, the arctan going to negative infinity is negative pi over 2, but be careful, there's also this other negative in front. And then, of course, the limit as b goes to infinity for the arctan will just be positive pi over 2. These two, of course, negatives become positive pi over 2 plus another pi over 2 would just give us pi. So kind of an interesting outcome again. You might have thought that an area that goes on and on forever in two different directions would still be infinity. But as it turns out, the area from negative infinity to infinity under this curve here is actually just equal to pi. And because of that, we can follow this answer up with one more little conclusion, in that since we're getting a finite number, not infinity, we can say that this integral converges. Okay, in these last two slides, we're going to take a look at the second type of improper integral. But before we talk about what type that is, let's take a look at the question that's going to get us to seeing that second type of improper integral with this question. We want to again find the area under the curve of 1 over x squared between negative 1 and 1. So I think we could have easily done a problem like this way back in chapter 4 once we understood that a definite integral was telling us to find area. So we can easily set up this integral from negative 1 to 1 of 1 over x squared. Just kind of recall again, this is not one of those natural log integrals. If we move this to the top as x to the negative 2 power, add 1 to the power, divide by that new power, and go through those steps, we'll of course end up with an antiderivative of negative 1 over x, and then we can apply the fundamental theorem of calculus. When we plug in the top bound and plug in the bottom bound and subtract, we should end up with an answer here of negative 2. So what's wrong with this answer? We're getting an answer and it doesn't seem to really be much of a big deal at all. Well, the problem is this, and you would have never saw a problem like this. It would have had different bounds maybe, but we would have certainly never saw an integral like this one, because what we need to realize is that this is an improper integral because there's a discontinuity inside this region where we're trying to find an area. And to show you that, here's a picture of 1 over x squared from negative 1 to 1. And you can see we have a vertical asymptote here at 0. Because of that, that's what's making this an improper integral. So how are we going to approach a problem like this? We don't have infinity that we need to get rid of as one of the bounds. I think with that first type of integral, those are fairly easy to set up since you know you got to get rid of that infinity as one of the bounds on your integral. So how are we going to do this problem? Well, the real area, or the proper integral that we need to set up here, is going to look like this. And the reason I have a 2 here in the front is, unlike that last example I did, I am going to go ahead and take advantage of the fact that we have symmetry here. I'm going to consider half of this picture, and then of course because of that, I'm multiplying by 2 so we can get the total. So the half I'm considering is just this right half right here. I just want to find the area of this right half, and that's of course again why I'm multiplying by 2 there. So then why are we setting up an integral from 0 to 1? Well, that of course is again that right half. But there's still a problem. This would be an improper integral because we know 0 is our vertical asymptote. 0 doesn't exist for this function. So that you can almost view as an infinity. This thing right here, it's not an infinity symbol, but that's the thing that's making this integral improper. We can't have that 0 there. So what we're going to do instead, just like you saw in the first type of improper integral, is we're going to get that bound out of there that's kind of messing us up. And to do that, I'm going to call, instead of some value off to the right, a or b or whatever, I'm going to put a value of a right here. The reason I'm going to put a value of a right there is because I want a to approach that value that's messing up our integral. Again, we can't have this bound of 0 here, but I can certainly have a bound of a. A could be, of course, 0.1, 0.011, 0.000011. It could be really any number as long as it's not 0. And what we want to do is we want to let that a approach 0. In other words, we want to take the limit as a approaches 0, and be careful, it's been a while since we've seen this. When there's a little plus sign right there, we're saying we're approaching 0 from the right. So be careful. We haven't seen that notation in a while for limits, but that's what that's saying. We want to approach we want a to approach 0 from the right side. And now we have what is called a proper integral. This thing right here is what really your goal is in terms of starting these problems. You need to write a proper integral, and then of course we can go through the steps of figuring out what all of that's equal to. So let's go ahead and go through those steps now. We of course already know what this integral is equal to since we did it above. So we know that the integral in this case, and keep in mind there's now a 2 here in the front, so that's why there's that 2 right there. The integral is negative 1 over x, but because of the 2, it'll be negative 2 over x, and then we have our bounds of 1 and a. We can apply the fundamental theorem of calculus now, plug in the top bound, so that'll be negative 2, plug in the bottom bound, so that'll be negative 2 over a, and then we subtract those two values. And just to help this a little bit more, I'm going to put all of that in brackets, because now we need to take the limit as a approaches 0 from the right side. So what's that going to look like? Well, you'll notice, of course, the negative 2 isn't affected by this limit since there is no a with it. And what you're going to have to recall back from our first days doing limits, I suppose, back in chapter 1, is that when we divide by 0, we're essentially saying infinity. It's not really equal to infinity, but it's the idea of infinity. When you divide 2 by 0, or any number by 0, we're really essentially saying infinity. And in this case, since there's a negative in front of this fraction, it'll be negative infinity. Bottom line is, when we take negative 2 and interact it at all with infinity, we're just left with infinity. We'll have negative 2 minus infinity, or instead negative 2 plus infinity, which is just infinity. And again, other than maybe those surprise problems where we actually got a finite number, this shouldn't be a surprise. If we want to find this area based on this picture you see here, it looks like it kind of keeps on going and going forever. Of course, the area would be something that I think everybody would kind of understand as being infinite. Again, the area under the curve of 1 over x squared between negative 1 and 1 is infinite. So to kind of round out the answer here, or to kind of make a conclusion based on this answer that we're getting, we can of course say that this integral diverges because it does not approach a specific number. We're not getting any sort of finite number here, so we can of course say that this integral diverges because its area is equal to infinity. Okay, one more example of this second type of improper integral. Why is this an example of an improper integral? Well, what this integral is asking us to do is to find the area under the curve between 0 and 1. If you need a little visual of that, here you go. We're trying to find the area from 0 to 1 under this curve 1 over the cubic root of x. So it's seemingly an innocent problem until you again realize that that x equals 0, or the y-axis, is a vertical asymptote. The integrand has an infinite discontinuity at x equals 0. Because of that, this 0 is making this integral improper. So we can't have that 0 there. What we need to do is make it a proper integral. And I guess before we do that, just to kind of make this look a little simpler when we're ready to take the integral, of course, we don't really want to leave this as 1 over the cubic root of x. We can move that cubic root of x to the top of the fraction there and make it x to the negative 1/3. The next thing we're going to do is get rid of the thing that is making this an improper integral. And again, that 0 is making it improper because that is a discontinuity. So instead, we're going to just put a letter a here because we want that letter a to approach 0. So that's what we're going to go ahead and do here. We're going to set up our proper integral here. This is again the key to all of these problems, or at least starting these problems, is setting up a proper integral. And then of course we can go through the process of figuring out the answer. So again, keep in mind a little bit of order of operations going on here. We want to do the integral portion first and then apply the limit. So how did we set up this proper integral? Well, again, we got rid of the 0 as one of the bounds and we called that a. And what we want to let a do is we want to let a approach 0 from the right side. Once we go through that process, we'll see if we actually get an infinite number, infinity, or if we get a finite number, which is again kind of surprising considering something can go on forever, and it turns out we get a finite number. So we'll see which one this falls into here in a second. Okay, so let's go ahead and take the integral. When we add 1 to negative 1/3, we get 2/3. When we divide by 2/3, which is never really a good way to leave it written, we can multiply by the reciprocal of that, or 3/2. So a nice easy integral, don't overthink that one. And now we can apply the bounds for the fundamental theorem of calculus. If we plug in the top bound, and actually let me put these brackets here so you can see all of that we're looking at as taking a limit of. When we plug in the top bound, 1 to the 2/3 is 1. When we plug in the bottom bound, a to the 2/3 is just a to the 2/3. And of course that 3/2 just sits in the front of that. Okay, now we're ready to take this limit. Of course the 3/2 is not affected by the limit. The 1 isn't affected by the limit. The only thing affected by the limit is any piece that has an a in it. And of course, we're letting a approach 0, which means we need to plug in 0. 0 to the 2/3 is of course just 0. 1 minus 0 is 1 times 3/2 is 3/2. So again, a very surprising answer. Something that's going on infinitely forever is actually giving us a finite number, and because we understand this concept to be area, we're seeing that the area from 0 to 1 under this particular function is a finite area. It's 1.5, 3/2. And again, as a follow-up conclusion to this, we can say that because we're getting a finite answer, we can say our integral converges.